So always remember the steps, the things that you have to find. Start an inventory, be organized in the way that you're doing your work, and you shouldn't have any problem. Okay, we have a function that is a little bit different than the other two that we've been working on. This one is rational, but notice that we have that root in the denominator here. With a root in the denominator, some sort of rational exponent in the denominator, typically that leads to two horizontal asymptotes that are different. So just keep that in mind as we go, and hopefully we'll be able to figure out what those two horizontal asymptotes are. Notice that if I was able to take the square root of the denominator, I'd wind up with a degree of 1 in the numerator and a degree of 1 in the denominator, which means that the leading coefficients would then dictate what the horizontal asymptotes are. Again, I'm giving you the first and the second derivative just to save time. Of course, on the homework, that's not going to be the case. You'll have to find the derivatives on your own, which is probably pretty painful, and I understand that. So the first thing we're going to do, the first thing that I do, is I look for vertical asymptotes. Is there ever going to be division by 0 here? No, because no matter what I do, I'm squaring a positive or a negative number, and then I'm adding to. So even if I pick up a negative number or 0, nothing is going to give me division by 0. So I'll just write vertical asymptotes, none. Next, we want to find either a horizontal asymptote or slant asymptotes. And in this case, because we know that when we take the square root of this, we'll have degree of 1 over a degree of 1, we know we're going to have horizontal. And because of the the radical in the denominator, I'm guessing there's going to be two horizontal asymptotes here. So to figure that out, remember the sort of rationalizing technique that we used. You can divide top and bottom by x to figure out what happens as x goes off to infinity. That's where we get our horizontal asymptotes from, limits at infinity. So if I plug infinity in here, I get infinity. If I plug infinity in here and then add 2 to it and then take the square root, I get infinity, which is the indeterminate form. Infinity over infinity lets me know that there is a horizontal asymptote here, but I have to manipulate the equation to be able to find it. So what I'm going to do is divide the top and the bottom by x. When I do that, in the numerator, I get 1 over the dividing by x here needs to be rewritten as dividing by the square root of x squared. That lets me sneak that x squared into the square root function. And now I have a big square root here. So then x squared divided by x squared is 1. So I have the square root of 1 plus 2 over x squared. So now I can plug infinity in, and I get 1 over, this goes off to 0, the square root of 1. Well, the square root of 1 is, in our case, plus or minus 1. So we wind up with 1 over plus or minus 1 for our horizontal asymptotes. This would reduce down to y equals 1, y equals negative 1 for horizontal asymptotes. Because of the fact that I have horizontal asymptotes, I'm probably pretty sure that I don't have any slant asymptotes here, but it's worth taking a look to make sure. Obviously, the degree of the numerator is the same as the degree of the denominator, which means no, there are no slant asymptotes. For slant to be there, there'd have to be a degree here that is 1 more than the degree here. Okay? After I find my asymptotes, I put them in. So I have plus and minus 1. In this graph, that's going to be pretty narrow. So I'm going to call this 1 right here and this negative 1 right here. And I'll put my horizontal asymptotes here. That way I can just see a little bit more detail. That's what we're dealing with. Now I have no idea what the graph does, but those are my horizontal asymptotes. Is the function discontinuous anywhere? No, it's not. So whatever I draw has to be approaching one of these asymptotes over here and approaching the other asymptote over here, and the function's continuous. So already this is definitely going to be kind of a weird looking function, I think. The next thing we should probably do is figure out y-intercepts and y-intercept and x-intercepts, if there is any. So to do y-intercept, we set x equal to 0, and that gives me 0 in the numerator divided by, I don't care in the denominator, it's not 0, So I get 0, 0. So I already have my x-intercept, or at least one of them. Maybe there's more than one, I don't know. I still should probably go ahead and find my x-intercepts. I do that by setting the equation equal to 0, and I get 0 equals x over the square root of x squared plus 2. Well, the denominator disappears again, and I'm just left with 0 equals x. So this is my only x-intercept, and it's my y-intercept. What's the next thing we should do? Okay, so we take the first derivative and we'll land here to save time. Obviously, this is a pretty ugly looking derivative here, so that saved us like 20 minutes worth of work right there. Set it equal to 0, and what happens? We'll get our critical numbers. So I divide, or I'm dividing by this denominator here. Multiply both sides by the denominator, and I wind up with, for f prime, I wind up with 2 equals 0, which is false. There's nothing to solve for, so what can we say? No critical numbers. What does that mean? What are critical numbers telling us? Well, it does cross the x-axis. What do critical numbers tell us? It gives you extremum, right? So when we have extrema, the graph is what? Yes. No. Changes direction. The slope is 0. Yeah. So what we're saying here with no critical numbers is that at no point on this graph is the slope equal to 0. Okay? So there never is a relative minimum or maximum value, which is interesting, I think. So this graph gets even more interesting. No critical numbers. Well, we should probably see if we have any inflection points, because otherwise we're going to be kind of sunk. Then we'll have nothing to talk about. So we set the second derivative equal to 0. The denominator again will disappear. So will that negative sign, and I'm left with 6x equals 0. So x equals 0 is an inflection point. So for my inventory over here, critical numbers, none. Inflection points, we have x equals 0. So it looks like all the interesting stuff happens right around here. Our y-intercept, our x-intercept, we have an inflection point, we have no critical numbers, we have horizontal asymptotes. What the heck is this thing doing? I don't have anything else to find here, so I can set up my intervals. My intervals will be what? Negative infinity to 0, and then 0 to infinity. Okay, so I need test numbers. Negative 1 and 1. I'm going to take those test numbers and plug them into the first derivative and the second derivative. Take negative 1 and plug it into the first derivative. Obviously the numerator is positive. The denominator, negative 1 squared is 1, plus 2 is positive, to the 3 halves is positive. So we have a positive divided by a positive. We are increasing. Take 1 and plug it in. Positive plus positive is positive. Positive divided by positive is positive. We're still increasing. Check concavity. Take negative 1, plug it into the second derivative. Notice the negative sign out front. Negative 1 in the numerator becomes negative. With that negative out front, the numerator is now positive. Negative 1 into the denominator. Negative 1 squared is positive 1, plus 2 is positive, to the 5 halves is positive. So we are positive, which means we are concave up. Now we take 1 and plug it in. Again, in the denominator, this is just going to be positive. But here with that positive 1 times 6, we get the positive with the negative out front, which makes us negative, so we're concave down. So now analyze what we're looking at. We are increasing in concave up. A graph that does that looks like this. we are increasing still, but concave down. A graph that does that looks like that. The function's continuous, so the graph here must be doing something like this. And then as x becomes infinitely huge, we approach that vertical asymptote. If I wanted to be more accurate, then I could pick a couple of numbers outside of there, like maybe -2, comma what, and +2, comma what. So just to be a little bit more accurate, we already know the graph is going to do something like this, but I don't know exactly how it's going to do that. So let's do this. Take -2 and plug it in. We get -2 in the numerator. Square root of 2 squared, so that becomes 4 plus 2 is 6, so the square root of 6. We have 2 divided by the square root of 6. Square root of 6 is like 2 point something. Okay, so we have -2 divided by 2.45. What's that? .81. Okay, so -2, comma 0.81. Positive or negative? This one's negative. What about this one? That one's going to be positive. Same result, but positive. Okay, so 0.81. Again, this is 0.5 right here. So we have -2, 0.5. We're going to be right about there. And then we have +2, 0.5, so we're going to be right about there. Now we can make a much more accurate graph. As we approach, we started off way down here towards infinity there, and we start to curve up. We switch concavity here without going vertical, or with going vertical, and there we go. So there's your graph. But it all comes from this information right here. So trust your math. As we were going along, we were getting some really bizarre results. But continue with the problem. You may be doing it right, and you can then come up with your graph. By the way, you could check this on a calculator. This is the actual answer, though. All right. Analyze and sketch the graph of this ugly-looking function. We have rational exponents. I've given you the first derivative and the second derivative to save time. We have rational exponents in both. It's a huge bummer, okay? So we can work our way through this problem, though, and we're going to work our way through this problem. And then you can go teach it to somebody. And yeah. So let's talk our way through this problem. What should we do first? Look for vertical and horizontal asymptotes. Good idea. So first of all, do we ever have division by 0 in the original function? No. There is no division at all. So vertical asymptotes? None. Horizontal asymptotes. Horizontal asymptotes spring up from rational functions. Do we have any of those? No. So there are no asymptotes to talk about. Likewise, slant asymptotes, we'd have to have a rational function. So there are no asymptotes at all. What can we do next? Intercepts? Okay, that's a good idea. So if we set x equal to 0, we get 0. So we do have a y-intercept of 0, 0. I can mark that on my graph right now. Okay, x-intercepts. Obviously, we have one already. Okay, good. If I set this equal to 0, now I have 2x to the 5/3 minus 5x to the 4/3, and that's equal to 0. Factor out least powers. The smallest exponent of 5/3 and 4/3 is 4/3. So we don't have a GCF between my numbers, so I'll leave that alone. I'm factoring out x to the 4/3 times what's left over, which is 2x to the, if I distribute 4/3 in, I gotta have 1/3 sitting here to get the 5/3, minus what? just 5. Equals 0, so 0 product property. This becomes x to the 4 thirds equals 0, which means x equals 0, which we already knew. But we also have this 2x to the 1 third minus 5 equals 0. No. Yes, move the 5 over and then divide by 2. And now I have x to the 1 third equals 5 halves. So that says the cube root of x equals 5 halves. I want just x. How do I get rid of a cube root? You cube both sides. So we cube here, we cube here. Now we have x equals 125 eighths. What is 125 eighths? Because we got to put this on our graph somewhere. 15.625. Okay, so I only have 7 grid lines here. 15.625. Maybe if I go by 2s. But if I go by 2s, then I'll be able to at least kind of guess where that is. Can I do that? Let's go by 2s. So I'm a hypocrite. What do you want? We're going by 2s here. That puts 15 right about there, and it was 15 point what? 0.62. So we're just a shade farther. I'm going to put my dot right there. Okay, it is curve sketching. It's not curve 100% accurating. Okay, so we can be slightly inaccurate here. The point is, can we do the math to get the graph? All right, so we have an x-intercept here. Remind me that we're going by 2s when we're doing anything on here, because I will forget. Okay? All right. So we do have x-intercepts. We already know that we have that one, but we also have 0, 15.6. Now what? Okay, critical numbers. So that means we're taking the first derivative. What's that? Oh, sorry, yeah, thank you. This should be 15.6, 0. Okay, so we've taken the derivative now, and we feel proud about the fact that we got this derivative. We set it equal to 0. So for f prime, what do we do? Well, first of all, since I set this equal to 0, I can get rid of that 10 thirds, right? Multiply both sides by 3/10 and it's gone. So then I can use 0 product property, and I have x to the 1 third equals 0. X to the 1 third minus 2 equals 0.
Why didn't you divide like that whole, the whole x by x, or 10 over 3x to the 1 third and got rid of it?
Can we divide by a variable, Jake?
Oh no.
No.
That would be why. Okay. I was just
0 product property splits it up. Never divide by a variable, okay? And even multiplying both sides by a variable is scary sometimes. So what does this become? 0. We cube both sides and we get x equals 0 for a critical number. Over here, we add 2 to both sides, and now we have x to the 1 third equals 2. So we cube both sides and we get x equals 8. Okay, so put that in the little list of stuff. We have critical numbers, no vertical asymptotes, so we have critical numbers of x equals 0, x equals 8. Now what? Look for inflection points. So we take this guy right here, and we took the derivative, and we simplified it down to this. We set it equal to 0, and now I begin my second derivative analysis. I didn't say that. I don't want to divide by a variable, but I can multiply both sides by the denominator to get rid of it. That's fine. If I multiply both sides by the denominator, it disappears. If I divide both sides by 20, it disappears, and I'm left with x to the 1 third minus 1 equals 0. So that means x to the 1/3 equals 1. Cube both sides, and I get x equals 1 as an inflection point. Okay? So I can add that to the list over here. We have an inflection point, which is x equals 1. All of those are used when we set up our intervals. Is there any other work that we need to do before we set up intervals? No? Okay. So we set up our intervals then. What are the intervals going to be? I'm going to write this small. Okay. Okay.
Oh yeah, 8.
1 to 8. Okay. And then 8 to infinity. Critical numbers and inflection points get included in this. Now we need test numbers. F prime, F double prime. You guys are good at test numbers.
One thing I get right all the time.
Even though you can pick any number that's in the interval.
Yeah. So we always pick 1/3 interval.
Yeah, if somebody were to pick one that's not in the interval, I'd be pretty upset. -6. What a great idea. No. Now, that brings up a good point, though. Because of these wacky numbers that we have here, you could pick numbers that kind of make your math easier. So the ones are always going to be easy. But over here, in this interval and this interval, not easy. How about -1 here? Now we want to pick something that's going to be easy there. Is 1/2 going to be easy? I have no idea. Remember, we are raising it to the 1/3 power. So we want something that we're going to be able to take the cube root of, probably. Or 1/8. Right? Okay, so think about these numbers before you put them down. Let's try 1/8. Hopefully that'll work out well. Now we want something we can take the cube root of here. It's got to be between 1 and 8, something we can take the cube root of easily. We have perfect cubes are 1, 8, 27. How about 27/8? Is that in the interval? Yes, it is. And now here, 27, something we can take the cube root of easily. Okay? So that's just a thought. You could always pick easy numbers. But when you do that, are you going to be able to analyze positive and negative? Maybe, maybe not. Okay? You might spend forever trying to figure that out. Okay, so let's carefully now plug in. I'm even going to change colors here because I feel like it. Let's carefully plug in these numbers into the first derivative and see what happens. So we take -1 up here. What do we get here? What's the cube root of -1? It's -1. So this becomes negative. What's the cube root of -1? -1. So we have -1 minus 2, which is negative. This is negative. Negative times negative is positive. So that means we are increasing. Take 1/8 and plug it in. The cube root of 1/8 is 1/2. 1/2 is positive. Times this is positive. This is 1/2. 1/2 minus 2 is negative. Positive times negative is negative. So notice that if you picked a weird number here, like 1/2, you'd be trying to take the cube root of 1/2, and you don't really know what kind of number that is unless you plugged it into your calculator. But if you have a calculator sitting in front of you, then why don't you just graph it on the calculator? Okay? So try to use smart numbers. We're negative here, so that means we're decreasing. Okay, 27/8. The cube root of 27/8 is 3/2 positive. Times positive is, this is positive. This is 3/2, which is like 1.5. 1.5 minus 2, negative. Positive times negative is negative. So we are decreasing. Next, 27. Cube root of 27 is 3. This is positive. Cube root of 27 is 3. 3 minus 2 is 1. Positive. Positive times positive is positive. We are now increasing. Second derivative. So hopefully our luck will still be with us when we're trying to evaluate these numbers. Take -1, plug it into the second derivative. What will this be? You can square then cube, or square then cube root, or you can cube root first and then square. Either way, your negative number is becoming positive. So the denominator is always going to be positive, because that'll be positive, this one will be positive, this one will be positive, this one is going to be positive. So the denominator is always plus. Okay? It's the numerator that we got to worry about. Now we're taking the cube root of all of these numbers again, which we can do. So it's going to be easy to evaluate now. So we take -1, the cube root of -1 is negative. Negative number minus 1 is still negative, times a positive 20 out front. We're negative, we're concave down. What do we get for this one? 1/2 minus 1 is, so we are negative, so we are still concave down. What do we get for the next one? 3/2 minus 1, positive. So we are now positive, concave up. And finally, positive, concave up. Okay, so now let's do the little analysis of what the graph must look like. Increasing, but concave down. Like that. Decreasing, but concave down. Like that. Decreasing, but concave up. Decreasing, but concave up. Like that. Okay, and then increasing, concave up. Like this. So now we have an idea of what the shape of the graph will be as we try to plot this. But here's another issue. Like right now, I could do something like this. Okay, that's generally what the shape's going to look like. But I have no idea. Already, I'm going by 2's here. I have an x-intercept way the heck out here. I have all of these critical numbers. I need to know exactly what the ordered pairs are for that one. I also have an inflection point. I got to have the ordered pair for that too. So I'm going to have to get these 3 ordered pairs here. This one I already have. It's 0, 0. So let me get that graph off of there. I kind of have an idea of what it looks like, but that idea is not good enough. Okay. One more little analysis that I want to point out to you guys. Do we ever have division by 0 in any of our original or derivative functions? Really?
Yeah.
Yeah, we do. In the first derivative, no. But in the second derivative, we do, when x is what? 0. So anytime you wind up with division by 0, you create horizontal or vertical asymptotes, right? But we know that we don't have a vertical asymptote in the original function. So that vertical asymptote here tells me that the function is not differentiable at that point. In order for a function to be continuous but not differentiable, it has to look like what? It has to look like a point, that's right. So we have this situation here, but it needs to look like a point when we get to this spot right here. So keep that in mind. Now, we want to come up with ordered pairs. We have 0, 0 already. We need 8, comma something. We need 1, comma something for our critical numbers and inflection points. Because of the pain I can see on your faces, let's do 1 first. It's actually not that bad. Take 1, plug it in to the original function. 1 to the 5/3 is just 1, so this turns into 2. 1 to the 4/3 is still just 1, so it's 2 minus 5, which is negative 3. So 1, negative 3 is on my graph. Now remember, I'm going by 2's. Did you remember? I remembered. I'm going by 2's, so here's 1, and then I don't have a scale yet for my y-axis. Based on this 8 right here and these big rational exponents, I'm actually going to hold off on graphing this just yet. But I know that as of right now, I have that inflection point right here. Okay? So we have 8. Plug it in. You can raise it to the 5th power first and then take the cube root. I do not recommend doing that. Take the cube root first and then raise it to the 5th power. So we have 2 to the 5th, which is 2, 4, 8, 16, 32. 32 times 2 is 64. Minus, okay, 8 to the 4/3. That'd be 2 to the 4th. 2, 4, 8, 16. So we have 16 here, and then 16 times 5 is 16 times 5. Did you say 80? Okay. So we have minus 80. 64 minus 80 is negative 16. All right. So I'm glad I didn't put that dot on there yet. We have 7 here. If I go by 2's, that would get me to 14. Close enough? No. Let's go by 3's. So we need 8, 2, 4, 6, 8, negative 16, 3, 6, 9, 12, 15. We'll call negative 16 right there. Then we have 1, negative 3, so 1 is here. And then we're going by 3's, so now that inflection point occurs right there. Inflection points are where the graph switches concavity. That's right. So let me get this mess off of there. All right. And let me put my dot back on there. Okay, so now remember I have this idea that the graph is doing something like, okay, so now that we have this on there, with that change in concavity, we can kind of see that it's going to do something like this. But the question is, what does this over here do? Does it look like this? Does it look like this? Does it look like this? I don't know. So what should I do? Draw all of them? No. We want to pick an ordered, we want to make another ordered pair over here so that we get a better idea of what the graph does on that side of the x-axis. So give me a number to pick. Negative 3.
Wait, no, because we're going to be plugging it back in. So let's go with like
negative 1. Don't make life any harder than it has to be. At least start with negative 1, and maybe we'll get lucky and it'll be this case right here, and we won't have to worry about it anymore. Okay? So negative 1 plugged in gives me negative 1 here, right? So that's negative 2 now. Then negative 1 plugged in gives me positive 1. Good. I can take the cube root of negative 1 first, but then I'm going to raise it to the 4th power, which is going to make it positive. So this becomes negative 2 minus 5, which gives me negative 7. So negative 1 is here. Negative 7 would be here's 3, here's 6, so here's 7. So it actually winds up being that case. All right. We could go further, but why? This is just going to be decreasing and concave down the whole time, or increasing and concave down the whole time. So it's going to look kind of like this. Now remember that we have that sharp point here. So let's try to get this thing graphed. We have increasing and concave down, so the graph must look like this. So I can start down here and come up. We're going to have a sharp point right there. Okay with that so far? All right. Then we are decreasing and concave down, so the graph must look like this. And then we hit that inflection point. We're still decreasing, but now we're switching to concave up as we get over to this critical number right here. So I need to be showing concave down with a sharp point, and then switch concavity as we work our way over here. And then that would be a relative minimum. My other x-intercept is all the way over there. I'm still concave up, but now I'm increasing. So I turn around and I come up, and there I go. There's my graph. We haven't seen a polynomial one yet. Here's your polynomial. seems like first derivative and second derivative are going to be very easy, right? But I'm going to throw a little wrench into it and tell you that if you're working with polynomials, the best move is to factor it first if you can. If you can factor a polynomial that looks like this, you will then be able to set up zero product property situations and find your critical numbers much easier. If you were to just take this derivative, you'd wind up with 4x to the third and blah, blah, blah. There's no way that you would be able to find those critical numbers. Okay? So we actually want to factor this. Does anybody know how to factor that?
Wait, so you factor it first and then you take the derivative of what you factored. Is that what you're saying?
Factor it first. Yeah. That's going to make life a lot easier, trust me, if you're dealing with polynomials. If it can be factored, factor it. Factor by grouping? Think so? Pull an x out of everything. So we have two ideas now. We could pull the x out of everything, or factor by grouping. No, we don't want to take the first derivative for sure. After we're done crying, go to the next slide. No. You always want to factor out a GCF, and we do have a GCF here, which is x. So we get f of x equals x times x to the third minus 12x squared plus 48x minus 64. Now what? Factor again? Well, yeah, keep factoring. Can the thing inside be factored? Actually, this is a factorable thing that's actually very easy to factor. This becomes f of x equals x times that. With pluses and minuses in there, I must have a minus sign. This is a perfect cube. 4 to the third is negative 64. Negative 4 to the third is negative 64. If you were to FOIL and then distribute again, you would wind up with that. It pays to know the factoring properties of perfect cubes. Anyway. So here is our original function now factored.
Hey, now we can just
So we'll get there eventually. Before we do that, it's factored. Where do we start? Asymptotes. Do we have any asymptotes here? No. So I can start my inventory again. Vertical asymptotes, none. Horizontal asymptotes, none. No slant asymptotes either. Now what? Okay, x-intercept would be, y-intercept, okay, 0. So we have 0, 0, right there. X-intercepts. Set this thing equal to 0. Zero product property. We get x equals 0, obviously. And then x minus 4 to the third power equals 0. Take the cube root of both sides and you get x minus 4 equals 0. So x equals 4 is another x-intercept. So we have x-intercept of, we know 0, 0, but we also have 4, 0. 1, 2, 3, 4. Okay, now what? Okay, take the derivative. So here's my original function right here in factored form. The derivative will be f prime of x equals how do we take this derivative? It's a product rule. F prime is 1 times the original g plus g prime times f. So that f will be out front. So then g prime is the 3 comes down times what's inside to the second power times the derivative of what's inside, which is just x. So there's your derivative.
Wouldn't it be 3x
by 1.
Oh, sorry.
So I could factor out least powers here, and that would give me f prime of x equals, the least power is x minus 4 squared times what's left over, which is x minus 4 from this, and then plus the 3x. So then combine like terms, and I get my new first derivative, which is x minus 4 squared times 4x minus 4. If I wanted to, I could factor that 4 out. I don't really want to. There's my first derivative. Second derivative. Product rule again. F prime 2 to the first power now times the original g. Okay, plus g prime f. G prime in this case is easy. It's just 4 times the original f, which is x minus 4 squared. Well, if you look, this is also x minus 4 right here, squared. So this becomes 2 times x minus 4 squared plus 4 times x minus 4 squared. What do you mean, where does the 4 go that was in the second? Oh, yeah, okay, I'm sorry. So this is slightly wrong. Let's see. We have, this is good. We have 4, no. This is right, isn't it? Is this right? Why not? Oh yeah, okay, I see what you're talking about now. So this is good here, this is not good.
Right, that's you can't factor it out to get 4.
Right. Here I think I'm being all clever. Get busted for it.
Shut down.
This is a minus here, this is a minus. I can factor out least powers though. Can I do that at least? Okay. Least power here would be the x minus 4. So then I'm left with the 4x minus 4 from this. I factored out a 2 out of that, so plus 2 times x minus 4. All right, so simplify that. 2 times x minus 4, parentheses, this becomes a positive 2x, so that's 6x, and then negative 4 minus 4 minus 8. That's f double prime of x. Minus 8 minus 4 is negative 12. Thank you. I got to slow down. Minus 12. Again, I could factor a 6 out if I wanted to. So the advantage to doing what we did with the factoring first is it made the derivatives more complicated. I don't know what that was. It made the what is going on? It made the derivatives more complicated, but now everything is already factored for us. So when we set this equal to 0, it's very easy to do zero product property here and here to find our critical numbers. Had we not done that, then we'd wind up with cubes here, perfect or a cubic trinomial. Not easy to factor if it's not a perfect cubic trinomial like we had right here, which it won't be. So then it'd be almost impossible for you to find those critical numbers.
So, if, for example, we had
So now that we have the derivatives, we can come back and set each one of them equal to 0 to get our critical numbers and our inflection points, if there are any. And when I do that, I can see that I'm going to use the zero product property there. I don't really have a whole lot of room here, so I'm going to scroll down. And we'll come back up when we can. Okay, so we zero product property this, and we have x minus 4 squared equals 0. 4x minus 4 equals 0. And this is for the first derivative. Square root both sides. Add 4 to both sides, you get x equals 4. Add 4 to both sides here, then I can divide by 4 and I get x equals 1. So I have critical numbers. Let me go back up. Start a critical number list. X equals, what was it? Negative 4 and positive 1. So negative 4, x equals 1. We didn't have any vertical asymptotes to talk about, so that's where we're at. Take the second derivative, so let me scroll back down, set it equal to 0. Once I do, the 2 disappears, and I have x minus 4 equals 0, 6x minus 12 equals 0. So then x equals 4 is an inflection point, and we have 6x equals 12, so x equals 2 is another inflection point. So I can come back up here, and x equals 4 is an inflection point. So let me draw a line here. And x equals 2 is my other inflection point. So I'll put IP on that. Okay, so now we have our inflection points and critical numbers. So we can set up our intervals. So let me scroll back down and set up a table since I'm having a room. And I'm going to change colors once more. So my intervals are going to be negative infinity to 0. Is that right? Yeah, negative infinity to 0. And then 0 to 1. And then 1 to 2. And then 2 to 4. And then 4 to infinity. Remember that critical numbers and inflection points are included both in these tables. I need a test number, and then I'm going to substitute into the first derivative and the second derivative. My test numbers for each one of these is going to be, let's see, negative 1 there, probably 1/2 here, and then maybe 3/2 here. 3 and then 5, just to keep our numbers simple. Okay, I'm going to go back up so that I can see both of my derivatives. I'll take out the first derivative here. We plug negative 1 in here. Doesn't really matter, we're squaring whatever we get, so that's going to be positive. Negative 1 times negative 4 minus 4, that's going to be negative, so positive times negative is negative, which means we're decreasing. Again, this is going to be positive for 1/2. 4 times 1/2 is 2. 2 minus 4 is negative, so we are still decreasing. 3/2 times 4 would be 12/2, which is 6. 6 minus 4 is positive. Positive times positive is positive, so now we're increasing. Plug in 3. Positive times positive is positive, we're increasing here. And then 5 times 4 is 20, so positive, we're still increasing here. F double prime, taking the same numbers, plugging them into our second derivative. This is positive here. We have negative 1 minus 4 is negative. We have 6 times negative 1, which is negative, minus, so we're still negative. Positive times negative is positive. We're concave up. 1/2 plugged in, this is negative. This is 3 minus 12 negative. So we're positive, concave up. Here we are 3/2, so that's 18/2, 9. 9 minus 12 is negative. But then 3/2 minus 4 is negative. So we are positive, which means we're concave up. Take the 3, plug it in. This becomes positive. This is negative, so we wind up negative, concave down. And finally, we have 5. This is positive. This is positive. So we are positive and concave up. Okay, so this is a polynomial. It's continuous. We don't have any asymptotes to talk about. So let's try to figure out what each one of these is showing. Decreasing but concave up. So decreasing but concave up. It must do this. Decreasing, concave up. Well, that's the same result. So we're still like that. Increasing, concave up. So that must look like this. Increasing but concave down. So we're looking like that. And then increasing and concave up, we're looking like that. So that's just forming our picture a little bit better. For these critical numbers and inflection points, we need exact ordered pairs. So I have to find ordered pairs for all of these things. Is that actually a negative 4? Where'd that come from? That is a critical number of 4. That's not a negative 4, positive 4. So we need ordered pairs for all of these. We have x-intercepts at 4, 0, so we already have that one. I take 1 and plug it in here. And I'm just going to shorten this up. We get 1 comma negative 27. I take 2 and plug it in, and I get 2 comma negative 16. I've already taken out the 4 and the 1 and the 0, 0 we have. So those ordered pairs have to be graphed. So we got to get all the way down to negative 27. We have 7 lines here. I need to go by 3s maybe, and then we'll just be off the graph a little bit. 3, 6, 9, let's say 21 here, 23, no, 21, 24, 27 is here. So 1, negative 27 is right there. 2, negative 16. So here's 2, and then 3, 6, 9, 12, 15. So there's negative 16. I think that does it. We are a 4th degree polynomial, so this will look like a W. So we're coming in. If I bring up my graph or my lines one more time, I got to match up with these. So I'm coming in like so. I turn, but I don't turn back around. I come down. I have an inflection point. Turn back around here. There we go. There's your graph.